Okay, so we have Boyle's law, or a version of Boyle's law. The final pressure times the final volume equals the initial pressure times the initial volume, and this is at constant temperature and amount of gas. So as long as those are kept constant, this equation applies. So let's look at the first problem. A volume of air occupying 5.67 liters at 16.5 atmospheres is compressed to a pressure of 35 atmospheres. What's the new volume? For these types of problems, or any that have several different terms, I like to write them or list them. So we have a volume occupying, so that would be the initial volume would be 5.67 liters. The initial pressure would be 16.5 atmospheres. The final pressure, so it's compressed, so what we end up with is 35 atmospheres. And the final volume is unknown. There's always going to be one and only one unknown. If you have no unknowns, then there's no problem. If you have two unknowns, we only have one equation to use, so we can't solve it. So go back and find there should always be one that's left over. So we have PF VF equals PI VI. And you might see these flipped around. Doesn't matter. It's just one side equals the other. So so we have, let's put everything in here. Well, first let's rearrange it. We're looking for this guy. So we have VF is equal to PI VI over PF. Now this is the way a lot of students like to deal with it. That's why I do it this way. Normally what I do though, I just put the numbers into this equation. Then when we're done, all that's left is that VF and I solve. But you can always solve for VF initially, algebraically, just leaving them in variables, and then plug in the values. So VI is 5.67. The final pressure is 35 atmospheres. And we want the final volume, so that should be in liters. Atmospheres cancel, so yep, that's right. So it looks good. Just make sure that you have everything listed correctly as far as what's the initial and what's the final. Because all that really can go wrong here is that you pick you put the numbers in the wrong place. And that's our answer. And that's a 7. Got a little messed up there. Second problem, a volume of air occupying 8.55 decimeters cubed. That's 1 liter. A decimeter cubed is 1 liter, but that's a different unit of volume. And at 678 torr is allowed to expand to a new pressure of 411 torr. What is the new volume in mils? And it should say at constant temperature. I left it off just so that we wouldn't take up too much room with the problem. But on the exam and most problems in the book, it'll state at constant temperature, so that you know that you're dealing with Boyle's law, but we know that. So let's write this in here. Volume of air occupying, so our initial volume is 8.55 decimeters cubed. You can change that to liters if you want. It's just 8.55 liters. Our initial pressure is 678 torr. Our new pressure is 411 torr. And we don't know what our final volume is. If we look up at the previous problem, we see that we would rearrange Boyle's law into this form. And then we put in our values. 8.55 decimeters cubed. The final, oops, yeah. And this is why I list them, because I almost wrote this number. If you just try to drag the data from the problem, it can get very confusing. So I like to label everything so I can go back and double check what everything is. Torrs cancel, and we're left with decimeters. But that's not the units that they want, but one thing at a time. So we have 14.1 decimeters cubed, which is liters. And then to change to mils, we just multiply through by 1,000. So this would be 1.41 times 10 to the 4th mils. I don't know if I'm on the page, so yeah. And that will be the deal. Let me double check that. 678 times 8.55 divided by 411. and the volume has increased from 8.55 liters to 14.1. It should go up because we've reduced the pressure, and that's what Boyles' law tells us. Okay, go to the next problem. And it's just different variations. There's not a lot we can do with the equation. There's only 4 variables. We have to solve for one of them, but the units can give us some trouble. So a certain volume of air at 98.5 kilopascals is put under a new pressure of 5.67 atmospheres, changing the volume of air to 4.11 liters. What was the original volume? Okay, so this time I gave you units that need to be changed immediately before we go into the equation. Because we have two, if one of the pressures was unknown, we could leave the units as is of one of these, but since both of them are given, they have to be in the same unit, so we got no choice here. So we have 98.5 times 10 to the third pascals. So this is our volume, initial volume, or initial pressure. So a certain volume of air, so that's what's unknown. And I'm just going to change this right over to atmospheres. You can already see, not mistakes, I mean I guess mistakes, but ones that I catch very quickly, but you can see that there's just so much going on in these problems. That's really once you have everything in the final form and you solve, it's easy, but getting everything into the final form is tricky. So as it shows, in that first statement, the initial volume is unknown. The final pressure is 5.67 atmospheres. And the final volume is 4.11 liters. So we got everything there. Now, the initial volume is going to be the final pressure, final volume, over initial pressure. And then we just put everything in. We have the initial final pressure, 5.67 atmospheres. Final volume is 4.11 liters. Initial pressure is 0.972 atmospheres. And I'm going to go double check everything here in a second. Let me see, 5.67 times 4.11 divided by 0.972. This comes up to be 24.0 liters. So, let's see. So we have initial. Yeah, that makes sense. Okay, so I was thinking this was the final volume, and it's the initial volume. It should be larger. And the final volume is going to be smaller because we've increased the pressure by almost about 6 times. So yeah, that definitely makes sense. Just stunned me there for a second. It's like, oh no. But that's why we list it. That's why we go back through, make sure everything is exactly what it should be. It's really the only thing that can go wrong here. Let's take a look at this problem here. And to save some room, I might write above it. So we have 6.77 meters cubed of neon gas. So that's another volume and is under 5.61 times 10 to the 4th millimeters of mercury pressure. What must the pressure change to for the new volume to be 1.5 times 10 to the 3rd liters? Okay, so it's a little awkward phrasing, but let's take a look here. So we have the initial volume is 6.77 meters cubed. The initial pressure is 5.61 times 10 to the 4th millimeters of mercury. What must the pressure change to? So we don't know the final pressure, but the new volume, we want that to be 1.50 times 10 to the 3rd liters. Okay, so we got a little work to do. Let's change the meters cubed to liters. There's 1,000 liters in a meter cubed. So this becomes 6.77 times 10 to the 3rd liters is our initial volume. And if you didn't know that, you'd have to take meters cubed and change to centimeters cubed. and then, or maybe to decimeters cubed. You have to work back, but knowing that there's 1,000 liters in a cubic meter, that will help you out. Otherwise, but you can certainly figure it out. So we have the initial volume, final volume in the same unit. So now we have to find, what are we looking for? The final pressure. So PI, VI over VF. So our initial pressure is, and it doesn't say that we have to be in any particular unit, so we'll leave them as is. We have 5.61 times 10 to the 4th millimeters of mercury. The initial volume is 6.77 times 10 to the 3rd liters. The final volume is 1.50 times 10 to the 3rd liters. Liters cancel, and we're left with 5.61 times 10 to the 4th times 6.77 to the 3rd divided by 1.5. And so this comes up to be 2.53 times 10 to the 5th millimeters of mercury. So even though that's a gigantic number, just remember we're dealing with millimeters of mercury, so it's not outlandish. If you had that for atmospheres, you'd probably want to go back and check. It's not impossible to have that on the exam, but it'd be or on the exam, but it's unlikely. But when we're talking about millimeters of mercury, that's not unreasonable. Okay, and then our last problem here, just give you a little variation, a little tricky guy here. 10 liters of argon gas is under a certain pressure. If the pressure is increased by 5 times, what is the new volume? So let's take a look here. We have our volume, our initial volume is 10 liters. Our initial pressure is unknown. What is the if the pressure is increased 5 times, what is the new volume? So our new volume is unknown. The new pressure is 5 times the old pressure. So it seems, okay, we got 2 unknowns, but now put it into the equation. And I put this because this is a very popular problem in homework assignments and on standardized exams. So if we put everything in that we know, we have, well, we need to solve, well, we don't know what we need to solve for yet. So we'll leave this. This is unknown. So PI, VI is 10 liters. PF is 5 times PI. VF is unknown. But we see that now, since we don't know what we started with as far as the pressure, but we know the final pressure is 5 times that. So since we have PI and 5 times it, these guys cancel. And so VF equals 2 liters. So it's a little tricky because it seems like we're missing something. But it tells us everything we need to know. If the pressure is increased by 5 times, so we don't know what the pressure was, but we do know the final pressure is 5 times that. If you put everything in, and you'll see that that initial pressure cancels. Even though we don't know what it might have been 1 atmosphere, it might have been 10 atmospheres, we don't know.